Hey guys, we are going to look at section 4.1, which is linear approximations and applications today. I know that this is less than ideal. I know this. Scooch that out of the way. And I apologize about the learning environment that we're in now. This is not our best, but please, please, please do watch over these. Send me questions. I'm not getting very many questions. A few of you are asking me lots, which is great. Ask me lots more. I haven't heard from some of you at all. So please don't be afraid. Send me an email. Send me a picture of your work. I can update it and send it back to you. Hey, Mrs. Turnley, how do I do this one? I'll write it out and I'll post it in Google Classroom somewhere. So the more questions you ask, the better off we all are. I'll share with everybody. So before we left, I gave you another packet. It was for Unit 5. I don't remember what color the assignment sheet on the front was. I didn't bring a copy home for myself. I feel like it was yellow, but I don't really know. So if you have the Unit 5 packet that I gave you right before we left, grab that. If you don't, you can mark up a PDF. I left it in Google Classroom, or you can print it out. It's up to you. So this is the assignment sheet that goes along with that. And then we're going to come down here. Here's my answer sheet. So starting our notes on page, this is probably page 5. I think this is page 5. Linear approximation and curve sketching. Now, I'll be perfectly honest, we're not going to talk about this first page. It's all about lines and how we can approximate a line when we get really, really close. Works much better in person than it does remotely like this. So we're going to skip over this. Don't worry about example 1. Example 2, we can start there. That's okay. The position, of an object in linear motion is given as s of t equals t cubed minus 20t plus 8. Estimate the distance traveled over the time interval from 3 to 3.25. So, distance traveled, how far did it go? We want an estimate instead of the real thing. What I'm going to have you do is start with your position function. S of t is equal to t cubed minus 20t plus 8. And when we take the derivative of position, do you remember what we get? It's been a while. It's velocity. So v of t is really 3t squared minus 20. My stylus is not behaving today. Good. So that's our velocity. But another way to write v of t for velocity is the change in position with respect to time. Kind of like that implicit differentiation or those related rates we were doing, is 3t squared minus 20. Now, to get the change in position, this is called our differential on the bottom. We're now allowed to move that. That's the different part that we're talking about today. I'm going to multiply it to the other side. So ds is equal to 3t squared minus 20. Use parentheses. Some of you are not very good with parentheses. Use your parentheses. Now, the change in position, another way to write change is delta. So delta S is equal to 3t squared minus 20 times delta t. So what's really going on here? We are approximating the distance traveled. This is the change in position. This piece in the middle is really the velocity times the change in time. So the change in the position is approximately the velocity times the change in time. So what we're going to do is come over here and use some real numbers. I'm going to switch colors. So delta S is equal to 3t squared minus 20 times delta t. The time that we're talking about is that initial time. It's the 3 seconds. So we put 3 in place of the t. 3 times t squared, which is 3 times 3 squared, minus 20. Delta t is the change in the time, how much time elapsed. Well, it's not 3.025, but it's 3.025 minus 3. So it's 0.025. Ran out of space. So delta S I've got my handy calculator. So I've got 3 times 3 squared minus 20 is 7. And 0.025. So 7 times 0.025 is 0.175. Now, that's the change in position, so we should have units. Our units were not given, we just have seconds. We don't have feet or inches or meters or anything like that. So that's okay, you can just leave it as is. So your change in position is 0.175. Pretty cool. These are probably the easiest, nicest word problems we have. A thin metal cable has a length L equals 6 when the ambient temperature is T equals 70 degrees Fahrenheit. Estimate the change in the length when T rises to 75 degrees Fahrenheit, assuming dl dt equals KL, where K is given as that constant. I've already told you what the derivative is in this problem, so you don't have to do anything else. You don't have to find the derivative. So you start out with dl dt is equal to KL. And then the new idea to remember today is that we can break apart these two differentials. That dt we're going to multiply to the other side. So dl is equal to KL times dt. And then you put in the values that you know. The change in the length, K is given, is 9.6 times 10 to the negative 6. Now that K would change depending on what kind of metal we had. That's the expansion constant. Length is how long is it initially? Well, it's 6 inches. And dt is the change in the temperature, not what the temperature is, but what's the change in the temperature. So that change is 75 minus 70, which is 5 degrees Fahrenheit. And then we'll use our calculator. So the change in the length is 9.6. Using my scientific notation, which is E. See the E? That button's right here on the comma. Second function, E, times 6 times 5. So that's what it looks like in my calculator. And when I multiply all those things together, I get 2.88 times 10 to the negative 4th. And the units here would be inches. Degrees Fahrenheit and inverse degrees Fahrenheit cancel out. So 2.88 times 10 to the negative 4th inches. So with that 5-degree temperature change, my piece of metal, which isn't very long, doesn't change that much. But you can actually see this. Bridges have expansion joints, especially ones that are all metal, if you've been across one of those. So in the summertime, they expand. And in the wintertime, they contract. But you have to make sure they don't contract so much there's a gap, or expand so much that it breaks the bridge. The power lines in the summertime, they're really droopy because that metal expands. And in the wintertime, they come up a little bit higher. So those are all things that engineers need to worry about when they're planning ahead. Let's see what else we have for examples. The Bonzo Pizza Company claims that its pizzas are circular with a diameter of 18 inches. What is the area of the pizza? And estimate the amount of pizza lost or gained if Bonzo's chefs err in the diameter by at most 0.4 inches. So we're going to start with a circle. Area formula for a circle. If we were in class, I'd ask you to remember that. Some of you would remember, some of you wouldn't. But it's pi r squared. Area equals pi r squared. So what is the radius? The diameter is 18. The radius would be 9. If I leave this in terms of pi, which is perfectly acceptable, the area is 81 pi. Some of you hate that pi symbol. You much more need a decimal. So 81 times pi gives me 254.469. And we're dealing with inches, so this is inches squared. Now for part B, estimate the amount of pizza lost or gained if the chef's error, that is a word, in the diameter by at most 0.4 inches. So let's switch colors here. So for part B, start with your area formula again, pi r squared. But this time we're going to take the derivative. So the change in the area, it's not moving, so it's not with respect to time, but it's with respect to the radius. dA dr is pi r squared. I'm going to multiply both sides by dr. The change in the area is pi r squared dr. All I'm doing is multiplying this dr piece to the right-hand side. It's multiplied to both sides technically. So the change in the area is pi r squared dr. So dA is pi. The radius, with the diameter is 18, the radius is 9 inches squared. dr is the change in the radius. Now, the problem statement says that the error in the diameter is 0.4. So what's the error in the radius? Well, it's half of that. You can take half of the error. So it's 0.2. So I am going to first multiply this and leave it in terms of pi. So I've got, I didn't take the derivative. I did a bad job. So we're going to take the derivative of the area, pi r squared. So the derivative of area with respect to the radius is 2 pi radius. So the exponent of 2 comes to the front. The pi just sits there. And then radius to the first power. Now this dr that's highlighted in green, we're going to move to the other side. So the change in the area is 2 pi r times the change in the radius. So the change in the area, now we put our values in, is 2 pi. The radius is 9. If the diameter is 18, the radius is 9. The change in the radius is half of the change in the diameter. So the error in the diameter, or the change in the diameter, is 0.4. So then the change in the radius is 0.2. So then we use our calculator and we multiply these together. First, I'm going to leave it in terms of pi. So 2 times 9 times 0.2 is 3.6 pi. And the units here would be inches squared because it's the error in the area. And then if I turn that into the decimal equivalent, some students just hate leaving it in terms of pi, it's 11. So the change in the area is 11.310 inches squared. So change, error, those are interchangeable for these problems. All right, number 5 is a circle problem again. The circle of a radius increases from an initial value of 10 inches by 0.1 inches. Estimate the increase in the circle's area. Choose a new color here. So we're going to start with the area formula. Just like above, area is pi r squared. We want to find the derivative with respect to the radius. So dA dr is 2 pi r. Then we're multiplying both sides by dr. That's exactly what's happening. Those cancel out. So the change in the area is 2 pi r dr. Now we can put our values in. The radius of the circle increases from an initial value of 10. So the initial value is 10. That radius increases by 0.1. Estimate the increase in the circle's area. So 10 times 0.1 is 1, times 2 is just 2 pi. But I have a feeling some of you are going to be more comfortable with your calculator. That's fine. 2 times 10 times 0.1 is 2. So 2 pi. Or if we want the decimal equivalent, not the answer in terms of pi, 6.28. So the change in the area is 6.28 inches squared. Very similar to the pizza problem, but sometimes it's helpful to see it again. These are probably the nicest, neatest little word problems we'll have all year. All right, that's example 5. Example 6, more round things. A diameter of a ball is 10 centimeters with a maximum error of 0.2 centimeters. Estimate the maximum error in the surface area and volume. So this is really 2-for-1 problem. We've got 2 things going on here. Let's start with surface area. The surface area of a sphere, and nobody ever remembers this, is, I just panicked, 4 pi r squared. So we want to find the derivative with respect to the radius. The change in the surface area with respect to the radius is 8 pi r. Then what we'll do is multiply both sides by dr, so the change in the surface area is 8 pi r dr. And then what we're going to do is plug in the values that we know. So the change in the surface area, or the error in the surface area, that's what we're looking to solve, 8 pi. The radius, they didn't give us the radius, they gave us the diameter. So if the diameter is 10, the radius is half of that, which is 5. The diameter has an error of 0.2, so the radius has an error half of that, which is 0.1. So then we can multiply these together. The change in the surface area, or the error in the surface area, the estimated error, it's not the real thing, is 4 times 5 is 40 times 0.1 is 4 pi. Again, you can do that in your calculator. 4 times pi is 12.56, and we're talking about surface area, so this is centimeters squared. So that is the error in the surface area. We are also asked to find the error in the volume. So the volume formula, that's what I almost said a minute ago, is 4/3 pi r cubed. So when we want to find the derivative of that, it's dv dr is 4/3 pi. Now the derivative of r cubed is 3r squared. Now the cool thing that happens here is look at your 3 in the denominator, 3 in the numerator. Those cancel. So the change in the volume, and I'm going to multiply dr to the right hand side at the same time, is 4 pi r squared dr. Then we put in our values. So dv is 4 pi. The radius, again, is 5. That change in the radius is 0.1. So 5 squared is 25. 25 times 4 is 100. 100 times 0.1 is 10. So dv is 10 pi centimeters cubed. If you're looking for the decimal equivalent, 3.14 times 10 is 31.4 centimeters cubed. All right. Again, very straightforward. They all work in the very same way. Find the derivative of that initial quantity, the volume, the area, with respect to that inside variable. And then just move that d bottom to the right-hand side. You're good to go. And here we go. Number 7, a tiny box is to be constructed in the form of a cube to hold 27 cubic centimeters. Use a differential to estimate how accurately the inner edge must be made so the volume will be correct within 1 cubic centimeter. So we're talking about a cube here. So here's my cube. Do you remember drawing these in middle school? There's my cube. Now, I know that the volume has to be 27 cubic centimeters. I also know that each side is exactly the same. That's what makes it a cube, not a rectangular prism. For a rectangular prism, you could have a different length, width, and height, but as a cube, they're all the same. So my volume equation is side cubed or x cubed. So we have to find the derivative. This is an easy derivative. dv dx is equal to 3x squared. Multiply both sides by dx, so dv is 3x squared dx. Use a differential to estimate how accurately the inner edge must be made so the volume will be correct within 1 cubic centimeters. So dx, that's how accurate that inner side needs to be made. The correct volume is 1 cubic centimeter. That's the value, excuse me, over here on the left. So 3, something's missing. I don't know what x is. They didn't come right out and tell me, but you can figure it out. The information is there. It's right here. I know that this box has to hold 27 cubic centimeters. So the volume must be 27 cubic centimeters. So how long does each side have to be? Well, I take the cube root. The cube root of 27 is 3. Just like square root, but cube root. So now I know x equals 3. So I put that in here. 3. Wanted to do something else there. So 1 is equal to 3 times 9, which is 27, dx. And dx is 1/27 centimeters. If you want that as a decimal, you can divide that out. 1 divided by 27 is 0.037 centimeters, which is our dx. So that is how we use differentials to estimate error or change in a certain quantity. Now the assignment. So the first assignment, which I believe I labeled as Wednesday, is worksheet number 1. Number 1 is a radius, so that's a circle problem. Number 2 is a circle problem. You're going to get stuck on number 2. Ask me questions about that one. I'll work it out and I'll upload it. I'm happy to do that. Number 3 is a sphere. We did one like that in our notes. And number 4 is a box. That's the example that we just did. So that's the first day's assignment. The next day is a sphere and a sphere, a cube problem again, and another sphere. So just break it apart, break that worksheet apart into 2 days so you're not doing too much. And then we get to talk about curve sketching, how we can look at these without a calculator. So I think that's pretty cool. So for the rest of the week, worksheet number 1, and then you can upload those. So again, email me, ask me questions. I'll help you out.